When you run a container, you type docker run nginx and it starts instantly. Inside that container, if you run ps aux, you see maybe 2 processes. But what's about your host? How does the container see a completely different reality? It's running on the same kernel, the same hardware, the same memory. What's really happening here? The answer is namespaces, a Linux kernel mechanism that creates isolated views of system resources. Today, we are going inside the kernel to understand how this works. Let's start with why namespaces exist. Back in the early 2000s, if you wanted process isolation on Linux, you had limited options. Cgroup for file system isolation. But processes could still see each other. Virtual machines gave complete isolation, but at massive overhead cost. In 2002, Linux developers began adding namespace support to the kernel. The first namespace, mount namespace, appeared in kernel 2.4.19, but it took until 2013 for all the pieces to come together, with user namespaces, and the latest addition, time namespace, landed in kernel 5.6 in 2020. Here is what makes namespaces powerful. They operate at the kernel level, not by wrapping or emulating anything. When a process makes a syscall, say get PID to get its process ID, the kernel returns different results based on which namespace that process belongs to. Same kernel, different views of reality. And this is the foundation of containers. When you run Docker, containerd, or podman, they're calling kernel functions to create namespaces. When Kubernetes creates a pod, it's orchestrating namespace creation and sharing. Understanding namespaces means understanding what containers actually are at a lowest level. Linux provides exactly 8 types of namespaces, and each one isolates a different kernel resource. Let me be precise about what isolate means here. It means processes in different namespaces get different answers when they ask the kernel about that resource. And namespaces provide visibility isolation, not security boundaries. They prevent processes from seeing each other, but they don't prevent attacks. Security comes from other mechanisms. Cgroups, seccomp, AppArmor, SE Linux. I'm emphasizing this now because it's the most common misconception. Okay, let me walk through each namespace type. I'll explain what it isolates and why that matters. First one is PID namespace. This namespace isolates the process ID number space. When you create a PID namespace, the first process in that namespace becomes PID1, the init process. That process can't see processes outside its namespace, and processes outside can't see processes inside. Here is what happens under the hood. The kernel maintains a separate PID tree for each namespace. When a process calls getPID, the kernel walks up the namespace hierarchy to translate the PID. From the parent namespace, you can see child processes with their parent-level PIDs. But from the child namespace, parent processes don't exist. Second one is mount namespace. It isolates the file system mount table. Each mount namespace has its own set of mount points. You can mount a file system in one namespace without affecting other namespaces. Critical detail. Mount namespaces support propagation modes. MS shared, MS-private, and MS-slave. And container runtimes use MS-private to ensure mounts inside containers don't propagate to the host. And this is how Docker can mount volumes without polluting the host mount table. Third namespace is network namespace. It isolates the entire network stack. Network interfaces, IP addresses, routing tables, IP tables rules, sockets. So this is huge. Each network namespace gets its own loopback interface, its own routing decisions, its own firewall rules. This is the foundation of container networking. Every container gets a network namespace with a virtual Ethernet interface connected to the host via veth pair. We'll demonstrate this in detail shortly. Next, IPC namespace. Inter-process communication. It isolates systemv IPC objects like shared memory segments, semaphores, and message queues, and POSIX message queues. So without IPC isolation, processes in different containers could communicate via shared memory, and it's breaking isolation. So next one is UTS namespace, Unix time sharing. It isolates hostname and NIS domain name. Simple but essential. It lets each container have its own hostname. When you set hostname in a container, you're only changing it in that UTS namespace. So, user namespace. This one is security critical. User namespaces provide UID and GID mapping between namespaces. You can map UID 0, so this is root, inside the namespace to an unprivileged UID outside. This is the foundation of rootless containers. A process can have root privileges inside its namespace, necessary for many applications, while having 0 privileges outside. And this mapping is configured via prot, speed, UID map, and GID map. So, kernel checks cap set UID in parent namespace to allow mapping. Next one, Cgroup namespace. It isolates the view of the Cgroup hierarchy. Processes inside a Cgroup namespace see their current Cgroup as the root. This prevents containers from viewing or modifying the host Cgroup hierarchy. And the last namespace is time namespace. It just isolates system clocks. This is the least commonly used namespace in production today. So, how namespaces are created? We have 3 syscalls that control namespaces: clone, unshare, and setns. Container runtimes use clone to create a new process in new namespaces. The unshare syscall moves the calling process into new namespaces, and setns is how tools like nsenter, docker exec, kubectl exec work. They join existing namespaces. So, here is your debugging superpower. Every process exposes its namespaces through directory, prots, pid, ns. Let's look at what this shows. These are special symlinks. The number in brackets is the namespace inode number. So, if 2 processes have the same inode number for a namespace, it means they share that namespace. So, this is also how you can debug container isolation. For example, pod containers can't communicate. You can check if they share the same network namespace inode. Or if process seeing things it shouldn't, you can check which namespace it's in. Most namespaces are flat. There is no parent-child relationship. But PID and user namespaces are hierarchical. For PID namespaces, parent namespaces can see child processes, but children can see parents. And user namespaces also nest, enabling cascading UID mappings. And this is how you can have nested containers, but it's rarely used in practice. So now let's see this in action. I'm going to create namespaces manually using the same tools that container runtime use. Every command here is what happens under the hood when you run a container. So let's start with PID namespace. First, I'll show you what the host sees. A lot of processes running on the system. Now I'm going to create a new PID namespace. Let me explain each flag. P. Create new PID namespace. F. Fork before executing bash. Critical because the forked child becomes PID1. And mount procs, remount procs directory to show only processes in this namespace. Look at that. We went from a lot of processes to only 2. And notice bash is PID1, where the init process in this namespace. Let me prove something. I'll check our actual PID from the host perspective. Same process, 2 different PIDs. This is namespace translation. The kernel is giving different answers based on which namespace asks. We're definitely PID1, and that comes with responsibilities. When PID1 exits, the kernel terminates all processes in that namespace. This is exactly what happens when you Docker stop a container. The container's PID1 exits and all processes are cleaned up. And the F flag is critical. Without forking, the unshared process itself will become PID1. Then exec bash and leaving no process to maintain the namespace. If you create a PID namespace without mount procs, you'll still see host processes. That's because procs directory is still mounted from the parent mount namespace. You need a new mount namespace and a remounted procs directory to see only your namespace's processes. Network namespaces are the foundation of container networking. I'm going to show you exactly how Docker connects containers to the network. First, let's create 2 network namespaces. These are persistent network namespaces. They are being mounted in var run netns directory, so they survive even without process running in them. Now let's see what's inside. Complete network isolation. No interfaces except loopback. This namespace can't communicate with anything. Now I'll create a virtual Ethernet pair. Think of it as a virtual cable. veth1 and veth2 are connected. Packets sent to one come out the other. Now I'll move each end into a different namespace. They disappear from the host. They are now inside the namespaces. So let's verify. Okay. Now I'll configure IP addresses. And now the moment of truth. Can NS1 reach NS2? Perfect. 2 completely isolated network namespaces, connected by virtual Ethernet pair. This is exactly what Docker does. Creates a network namespace for each container, creates a veth pair puts one end in the container and one end in the Docker 0 bridge on the host. Let me show you the routing table. This is real networking isolation. Each namespace has its own routing table, its own IP tables rules, its own sockets. When Kubernetes creates a pod, this is the foundation. Isolated network stack connected to the cluster network. Next one, mount namespaces. Let you change the file system view without affecting the host. Watch. I'll create mount namespace. I'm now in a new mount namespace. The M flag creates a mount namespace. Let me prove I'm isolated. I've mounted a TMP FS file system. Let me write some data. Now I'll exit this namespace. Directory exists but is empty. The mount is gone. The mount only existed in that namespace. The host file system is unchanged. And this is how containers can mount volumes, create overlay file system, and modify their file system view without affecting the host. Next one is user namespaces. As I said before, they are security critical, and they'll let you run processes as root inside the namespace, while they are unprivileged outside. Here is the magic. I'll create a user namespace as a regular user, no sudo. The U flag creates a user namespace, and the R flag maps current user to root. Now let's check. I'm root inside this namespace, but watch what happens when I try to affect the host. Permission denied, while not really root. Let me show you the UID mapping. This says UID 0 inside the namespace maps to UID 1000 outside, for a range of 1 UID. For example, applications that require root privileges can run as root inside the namespace. They can bin the privileged ports, change their own UID, manage their own processes, but if they escape the namespace or try to affect the host, they have 0 privileges. This is the foundation of rootless containers, Podman or rootless Docker. The container process runs as root inside and unprivileged outside. So, finally, let's connect everything to real containers. I'll run a Docker container and inspect its namespaces. Look at the inode numbers. Now compare with my current process. The container has different PID, mount, network, IPC, UDS, and Cgroup namespaces, but same user namespace and time. Docker by default doesn't use user namespaces because of complexity. Now let me enter the containers network namespace. So I can see the containers network interfaces without Docker exec. And this is exactly how Docker exec and kubectl exec work. They use setns syscall to enter the containers namespaces. Understanding this gives you debugging superpowers. You can inspect any containers namespaces without container tooling, just using cross-directory and nsenter. So, we have two network namespaces, host and container. The lsns command shows all namespaces on the system, and sometimes it's incredibly useful. Now let's connect namespaces to Kubernetes. A pod in Kubernetes is not a single container, it's a group of containers sharing specific namespaces. When Kubernetes creates a pod, here is the sequence. First, kubelet calls the container runtime, for example containerd, to create a sandbox. Then runtime creates a depose container. a minimal container that does nothing but sleep. Then, the post container creates network, IPC, and UDS namespaces. And then, all application containers in the pod join those shared namespaces, but get their own PID and mount namespaces. And this is why containers in a pod can communicate via localhost. They share the same network namespace, meaning the same network stack, same loopback interface, same IP address. PID namespace sharing is optional. You enable it with share process namespace true in the pod spec. When enabled, all containers see all processes in the pod, but I've never used this. And namespace operations have performance impacts you should understand. Every packet through veth pair incurs context switch overhead. So CNA plugins using eBPF like Cilium can reduce network namespace overhead by processing packets at kernel level before namespace boundary checks. Let's recap what you have learned. Namespaces are Linux kernel features that creates isolated views of system resources. There are exactly 8 types, each isolating different resources: PID, mount, network, IPC, UDS, user, Cgroup, and time. You haven't seen how to create namespaces manually using the same syscalls that container runtimes use. You understand that prod speed and s directory is your debugging interface. Compare inode numbers to see which processes share which namespaces. And you understand how this connects to production. Kubernetes pods are groups of containers sharing network, IPC, and UDS namespaces. When you kubectl exec, you are using setns syscall to enter those namespaces. And when debugging networking issues, you're debugging namespace isolation and veth pair configuration. And here is the key insight. Containers are not magic. They are processes with isolated views of kernel resources via namespaces and resource limits via Cgroups, which we'll cover next. When you understand namespaces at the kernel level, you understand containers. When you understand containers, you understand Kubernetes pods. In the next video, we'll cover Cgroups v2, the resource control mechanism. Namespaces give isolation, Cgroups give limits. Together, they form the complete container foundation. We'll also dive into container networking primitives, deep diving on veth pairs, Linux bridges, and how CNI plugins build on these foundations. You now understand the isolation foundation of containers, and everything else builds on these primitives.